Ladies and gentlemen, do we agree that slow websites suck? Yes. You could be more wild than that. Like, you could, like, raising hands, it's quite polite, but yeah. I've seen wilder audiences, let's call it that. Second statement, do we agree that web performance is an essential part of the user experience? Yes? Okay, this is getting better. Third statement, in my experience, slightly more controversial. Let's see about that. Do we agree that a slow website is just as bad as a website that is completely down? Yes, no, maybe. Meh is the words I tend to hear a lot in this statement. Regardless of your opinion, because the next things I'm going to tell you, take your opinion, don't take it for granted, is when your website is slow or down, you lose money, you lose face, you might even lose a little bit of Google PageRank in that case. So the question that we ask ourselves then is, how do we tackle this? How do we solve this? How to optimize this? And a lot of people look at the symptoms, slow websites, probably associated with capacity issues, and they throw servers at the problem, add servers, try to make it faster that way. And while on a short-term basis, when the house is on fire, you need to do some firefighting. And I support that statement. However, in the long run, this is not sustainable, and you're just throwing money at a problem. And as the famous poet, Notorious B.I.G. once said, more money, more servers, more problems. So you might want to get out of that one. So I'm going to ask the question again. I'm going to ask it 3 times. Second time I'm asking is, how do we tackle this? How do we really solve these type of issues? And the answer would be identifying the slowest parts and optimizing accordingly, right? It's a very sensible way of approaching it. Look at what's slowing you down, try to fix it, and you'll probably get some gains. However, in the long run, you might hit the limits. The point of diminishing returns, as we call them, where the amount of money and effort you put in to make it faster doesn't really result in the same output, definitely when the scale increases. So last time I'm asking the question, what do we do? Well, the answer, or my answer would be, why not consider caching? And I tend to use the analogy, the metaphor of boxes. Caching is nothing more than storing pre-computed stuff in boxes for later use. That's what I'm going to talk about from an HTTP perspective. That being said, hi everyone, pleasure. Thank you for being here with me. I know we have options. My name is Thijs. You chose to be here with me today. I'm going to try to make it as entertaining as possible. But as always, I'm not offended if you run out. I'm the technical evangelist at a company called Varnish Software. By a show of hands, who's heard of Varnish Software? It's not bad. I was expecting way less, because not a lot of people know our company. We're doing our best to increase our profile, like we create enterprise-grade software, but most people know us from the popular open source cache, Varnish Cache. Who's heard of that? See, more people, slightly more people. That's a good thing. Now, a lot of people use our technology, about 10 million active websites last we counted using certain software, 10 million active websites and 22% of the top 10,000 websites. So if you ask us what do we do, yes, we make the web faster. That's what we do. However, and that might be surprising, we also, it's a bit of a marketing term, but then again, I'm a tech evangelist, I work for marketing. We enhance digital experiences by lowering network latency, which is an evolution from making the web faster as a typical web performance play, moving and venturing into the world of content delivery. Not like our friends, we have friends from Fastly here and from Akamai here. They're full-blown CDNs, we just provide the software to build your own CDN. So in fact, we build software-defined web acceleration and content delivery solutions with the emphasis on software-defined. And the last thing I'm going to talk about that is our little claim to fame. It's a statement made by Intel, not by us, but we're just happy to repeat it as much as we can. Intel benchmarks have shown that we can process 1.3 terabits per second on a single machine, which seems to be, last I heard, a world record. Now, it's a moving target. I'm pretty sure someone will catch up, so we need to make sure we're on the ball. 1.3 terabits per second seems like tremendous. Will you ever need it? Well, our stats show that a lot of people do need it. But it's not only about that number on the left, it's also about that number on the right. It translates in 1.17 gigabits per second per watt, which is more of an efficiency thing. So talks about sustainability, of course, but also about power efficiency and doing more with less. I'm the author of Getting Started with Varnish Cache, which is an old book. I do not recommend buying that or reading that. I do recommend reading this one, which is my new one, Varnish 6 by Example. And as it happens, I have a free copy to raffle. It's a pretty big book, 778 pages. I wrote it during the COVID lockdowns. The lockdowns were long, as you might imagine, so it's big output. So what I'm going to do is I'm going to put this here. and I'm assuming that by the end of this presentation it'll be gone. I don't want to drag it on the plane anymore. So caching. Why would you like to cache? Why would you cache? Why would you even consider it? Well, if you look at the state of the internet and what performance issues at hand, we have a lot higher concurrency than back in the day. Like if you look at the last 20 years, now we're in a position that everyone can contribute to some successful web page, some successful app or a platform. All of a sudden you could get flooded by traffic. Handling that concurrency, if we refer back to the point of diminishing returns, if you solely do that by optimizing your code and your stack, you're not going to get there. Throughput's also a major factor. I think our CDN friends will acknowledge that the majority of the traffic on the internet is video-based, and we somehow need to deal with that. Higher throughput requires pretty strong infrastructure, and we don't want to throw servers at the problem. We want to do it intelligently, and caching can do that. And of course, when you work with these type of workloads or more real-time API-driven workloads, you need very low latency. And that's where caching comes into play to ensure that you don't recompute. So it's about improving the quality of experience, but it's also about something, if we take it to the more philosophical domain, why would you recompute stuff if the data doesn't change? Imagine you have a website that comes out of some sort of a CMS or a framework, and where the origin data is in a database. So you send a request to the server bootstraps the application runtime, and then the modules and the framework and the code, and then it needs to connect to a database and send a query and wait for it to respond, and all of that every single time. It has to flow all the way back for data that typically doesn't change. I mean, your contact page on your website powered by a CMS, it doesn't change that much. So why recompute it? Why waste CPU cycles, memory, network, and I/O on that? Might as well cache. So there's a variety of caches you could use, and yeah, I'm not going to go over the list. You can read, you can see it for yourself. What I'm going to talk about is a very specific use case. It's HTTP-based caching. And in a typical scenario, there will be a direct interaction pattern between the user and the server. We can use different kinds of caches. The browser still has the browser cache with all the good and the bad. You're probably well aware of that. But the server can also cache. The reason why it's important that the server also caches, maybe on top of the browser, is because of this pressure that could build up. If we don't provide the necessary caching at the server level, the concurrency or the type of workloads that are initiated could set the data center on fire. I've been to data centers where it was really, really hot, hotter than it should be. So what you do is you put a proxy in between, and the proxy acts on behalf of the server towards the client, and on behalf of the client towards the server. And sometimes both parties don't really have an idea that there's something in between. So we call these caches reverse caching proxies, with the emphasis on reverse. They're not the proxies like back in the 90s, early 90s, that you put in the office because the internet was slow. No, we have broadband internet these days, so we need to protect the servers from that impact. Those servers we often refer to as the edge because they're the outer tier of your web platform, the first thing that gets into contact with the end user. And that could be Varnish. Like, I work for Varnish software, so that could be Varnish. Could be anything else. Could be a CDN, or it could be a competing proxy technology. We also refer to the server as the origin. That's where the data originates. That's where everything is built up. Now, I heard Robin complain about the lights yesterday. I could see you pretty well. And you look confused to me, ladies and gentlemen. You look confused. So I'm going to untangle that by placing that image in there. This is a movie. Who's seen this movie? Who's old enough to remember it? By show of hands. Whew, young audience, I would assume. What's the name of this movie? The Bodyguard, featuring and Whitney Houston, indeed. And I like to use that metaphor for caching. So Whitney plays this very successful singer, actress that brings quality content to the stage, right? But she's so successful that she struggles to keep up with all the requests from stocky fans, so she needs a bodyguard to protect her. And Kevin Costner in that movie rises to the occasion and protects Whitney Houston. You probably remember the soundtrack, right? Wonderful. So whenever in doubt, whenever you're confused about caching or you're forgetting about it, think about the bodyguard, think about Kevin and Whitney. Now, last thing before we dive into the nitty-gritty is, I've done this presentation before and I got a little bit of criticism that it was Varnish-oriented. Now, I'm going to mention that the domains of application for me are a Varnish cache, but use your imagination, apply it to a CDN, apply it to another cache. And for this occasion, I tried to trim out the implementation-specific bits, because every cache has implementation-specific bits, which can be wonderful, which can be annoying. And for the end user, it could be annoying if they want to switch from one to the other. Luckily, and this is the crux of the entire presentation, HTTP has built-in caching mechanisms that are part of conventions, part of our RFCs. You can use those. Here's an old one, old but gold, the expires header. I wouldn't recommend that you use it. It's still out there, and in a very absolute way, it describes when it expires. So it's valid until Monday, the 20th of February, 2023 at 9:31 GMT. That was the last time I presented this talk. That was up in Canada for the Confu conference. Now, what I want to tell you about this one, it's very limited in terms of options, so maybe there's a better way, and the better way, you've probably heard of this one, is the cache control header. It has a very rich syntax and allows you to express your needs in terms of caching in a very explicit way. So you could use this one to say that content needs to be cached for 500 seconds. You can use that one to say that it can't cache your output. Now, before we go into the individual aspects of it, there's some key caching concepts that we need to talk about before we can continue. Again, what is caching? I'll read it off verbatim. Hold the response and serve it again upon subsequent requests. We've reached the point where we should be okay with that. But you have different kinds of caches. You have a private cache, and hence a private keyword that you can use. And that's a cache that exists in the client. Could be the browser, could be another device. And the reason why it's private and that matters in terms of caching is it is allowed to store very private data, whereas a shared cache, it can't because it's used by multiple people. So if you put very sensitive data in there and you cache it, well, that could be a problem. There's this famous story of a tax platform where a tax return was cached, and everyone who logged in to see their own tax return saw that one person's name. Like, it was horrible. So that's why, little side note, do not store personalized data that is very specific and targeted at one person. Then you have the time to live, which is the amount of time something is considered fresh in the cache. When that time to live expires, well, then the content is stale. So fresh content is content that hasn't expired yet, and responses can be reused and served. When the TTL hits 0, it's a moving target, right? The TTL goes from whatever you set to 0, and it could go below 0. It's that moving target. Well, then when it hits 0 or less, then it's stale. It doesn't mean you have to remove it from the cache at all. You could do with it whatever you want, and we'll have some good use cases there, but it requires revalidation. And revalidation means asking that origin server from time to time, like, hey, whatever I have, is that still the most recent version, or do we need to update it? And that's how that goes. In terms of the syntax, there's a lot of stuff in here. Most of it I'll cover, not everything, but I think there's even more than what I listed. So the cache control header has a lot of directives for you to control exactly how the cache should behave. So let's start with this one. Let's see if this works between us here. I'll throw something on the slide, and if you want, you can react. We can turn it into some kind of quiz. If I notice that there's not a lot of appetite for it, I'll turn it into a lecture. We'll see how we fare. So cache control public. Any idea what that will do? Any takers? No takers. Yeah, this is the way it's going to go, right? So caching is allowed both by private and shared caches. So anyone can basically cache it. For how long? Well, that basically depends on the default TTL in the implementation. So remember, private is the browser, shared is the proxy server. So again, if you want to see that in a visual way, private and a public cache. So you could say private, and then the content is still deemed cacheable. Caching is allowed, but only by private caches. We've seen that one before. Here's an interesting one that I haven't used, but that exists. You could say private equals set cookie. Let's see. Anyone have an idea what that one does? Crickets. No. But I appreciate your enthusiasm and your level of participation. Caching is allowed by all caches, so it is public until that set cookie header pops up. As soon as the set cookie header, because set cookie sets state, so we don't want to cache that in most cases. So as soon as that set cookie pops up, content is deemed private, only the browser can cache it, proxies need to back off. And then we have this one. All right, you should be able to handle that one, right? What will happen here? We see the keyword public, which means everyone can cache it. Max age is 100, which means 100 seconds of caching. Wonderful. We're building it up. We're getting that connection, right? It's happening. So yes, all caches allowed content is fresh for 100 seconds. And then, yeah, similar, I won't put you through that again. Yes, only browsers can cache, but for 100 seconds. So you're deviating from the default value. Here's where it gets interesting. What about this one? I'll give you a little hint up front. Naming things is hard. It's really hard. Naming. Why the hell did the powers that be went for S-max H when the previous one is max-H? Again, naming. Everyone remembers that expression. What's hard in computer science? Yeah, invalidating cache. That's a different talk. So if you're interested in that, dear people of the committee, book me next year. I'll talk about cache invalidation. So what happens here? Yes, but you know all about that, right? So he's cheating. He's an expert at the domain. So the S, and there's more experts in the room, S stands for shared. So that means all caches are allowed to cache it, but the shared caches will cache it for 100 seconds. What about the private caches then, you may ask? Well, they rely on the default value in the browser, I would say. And then you could combine it, and I won't put you to that again because we've already established that S-max H is for shared devices. I usually throw that in a slide when I do like basic Varnish presentations, and it always confuses people. And when I ask, how long will the cache, like the Varnish cache, the reverse caching proxy, deal with this in terms of caching, everyone falls into the trap and says 60 seconds because they know max H. The real answer is, yes, a reverse caching proxy will look at the max H, but if there's an S-max H, that will get the priority. So a shared device will cache it for 100 seconds. Your browser may opt to cache it for 60 seconds, as I've explained here. Now, what's also interesting is in predicting how long things will still be cached for. And a lot of caches use the H header to expose that. So this H header has 40 as a value, 40 meaning it's been in the cache for 40 seconds. And the max H says it can be in the cache for 60 seconds. So if you apply some very quick and simple maths, we end up that we still have 20 seconds of caching left before this thing starts becoming stale. And we'll talk about the impacts of staleness. So remember, remaining TTL, so when I refer to TTL, it's not always that 60 seconds or that 100 seconds that was set, but I'm often referring to it as what is remaining in terms of TTL. It's a TTL that was set minus the H. Now we talk about revalidation. So when something becomes stale, well, we need to revalidate it. And it's pretty much in most cases, from a private caching point of view, of course it's the user talking to the proxy. But since we can't really trust that, we would go from, hey, proxy asks origin, whatever I have here, is that still valid? And that would typically happen over a pretty basic, I'm using HTTP 1.1 here, it could be H2 or whatever, asking the origin, hey, I'm requesting this content, and the origin will respond, hey, well, here it is, 200 OK, store it in the cache, and go ahead and continue serving it. But there's this thing called conditional requests, which I'm a big fan of. And it all relies on a specific HTTP status code that we want to leverage, and it's called 304 not modified. As it goes with these types of headers, this doesn't contain any payload. It pretty much says whatever you have, it hasn't changed. Keep it, keep working with it. And the way a origin server knows whether content has changed or not and whether it should return a 200 or a 304 is dependent on certain other headers we can use. I like this one a lot, the ETAG header. So as either an application developer or a systems operator, you should, or in my opinion, you should emit an ETAG for your content. It's a unique value. There's no real syntax to it. It could be a number, it could be a string. I typically, in the frameworks I operate, I take a hash of the content, an MD5 or a SHA, and use that as an ETAG, because it's a pretty easy way of identifying it. So what will happen is your browser will be clever with that. So will most reverse caching proxies be, and they'll store that value and present it again upon revalidation for subsequent requests. So all of a sudden, your browser will do that, send an if non-match header containing that value and say, hey, this is what I've last got. Is it still valid? And if it's still valid, it'll be 304 not modified, and you can end it there, which is a very efficient way of revalidating. Because remember, in this caching content, we want to alleviate the pressure from the origin. So that means we want to do the least amount of requests, and we want to ensure that the requests we send it are very low impact. This is an excellent way of doing that. If you don't want to use e-tags, you could still use the last modified header, which states the exact timestamp of the last changed content. And then your browser will store that and present it using an if last modified header. Pretty cool. Now here's the tip and the trick towards you. Yes, please use that, but there's so many other benefits to it. So what I would say is validate quickly and exit early. What that means is, in your stack, whatever your role is within the organization, go home and ask your people to find a mechanism, maybe in the framework, to validate those e-tags quite quickly. So that means whenever the e-tag comes in, under the form of an if-non-match header, try to figure out if it's the most recent version, and if it is, stop whatever you're doing. Exit. Don't run the rest of your code, don't bootstrap your framework, don't talk to databases, because we already know the data didn't change. So why waste all those resources? My tip, the way I like it, is maybe in the pre-hook, before the entire framework or your entire stack gets bootstrapped, maybe store it in Redis. It's a distributed cache, it's pretty fast. You can do it in local memory if you don't want to do it distributed. Store the URL as the key, plus some variants that you want to keep track of, and then the e-tag value there. If it matches, stop whatever you're doing, exit, return, and there'll be not only no data over the wire because of the 304 not modified, you will consume less CPU, less IOPS, less network, less memory. So what that allows you to do is actually lower the TTL if your workloads are more real time. You can then say, instead of caching this for an hour, because we want to spare the server, you can cache it for like 5 seconds if you want, because the impact of that revalidation is tiny. And also, and a lot of caching systems have that, including ours, is if content is stale and 100,000 people are trying to access that, it won't result in 100,000 connections to the origin. Typically, it would be converged into a single request, which, if you play your cards right, will be very, very low impact. So, important tip from my end. The revalidation that you can do can also be asynchronous, and that's where stale while revalidate kicks in. So let's say you have a TTL of an hour, it expires, the unlucky user comes in, sends a request, and then what do you do? Do you say, well, you have to wait until it comes back from the origin? Could be the answer, but what you could also do is say, content is stale, but we'll keep serving it, keep serving the old stuff, while we asynchronously revalidate that, send an async fetch to the origin, and ensure that the users aren't penalized for it. And you can control the tolerance in terms of staleness through this stale while revalidate directive. So if you mention that, so in this case, again, the TTL is a moving target, right? So when it starts at 3,600 due to the max age, when it hits 0, well, then it becomes stale, but you can add the stale while revalidate value, and you're still at a number that's higher than 0. So you could still serve the cache while we asynchronously revalidate. So here's the definition. All caches allowed, content is fresh for an hour. Stale content can be served up to 100 seconds past the TTL while doing asynchronous revalidation. Now the thing is with that async revalidation is that people tend to abuse it for error cases. Let's say you have something in the cache, it expired, you need to revalidate, but your origin has gone up in smoke. It doesn't work. So you can keep sending the stale stuff. A lot of people abuse stale while revalidate for that by setting it to like an enormous number. My advice would be to use stale if error, which is also part of the cache control header, and you could set different values. So in this case, yes, all content allowed, cache for an hour. Stale content can be served up to 1 day past the TTL while the origin is unreachable, which is an excellent way of dealing. It's better to serve old content than to be serving 500 errors, I would say. Here's a little trick you should remember. So fresh content, the TTL, the remaining TTL needs to be higher than 0. Async revalidation can only work if the remaining TTL plus the stale value that was assigned is still higher than 0. If that is not the case, then you have to do synchronous revalidation. A lot of caches will remove the object from the cache, so you have to start from scratch. We in Varnish have this counter called the keep time that you could keep objects around. The reason why you would do that is you could still leverage the E tag and do conditional revalidations. So that's that. So remember, all these revalidations can be done conditionally. If you don't want to do any of that, if you want to force revalidation to happen and you have no tolerance towards staleness, you can use the must revalidate keyword. I've done a webinar couple of weeks ago about financial institutions and their challenges with caching. They're under regulatory pressure to always return real-time data. Caching is allowed for them, and they rely heavily on very active and granular cache invalidation, but they're not up for staleness. Let's say you have this stock website that displays share prices, stock prices. Well, they don't want things to be like stale for 10 seconds, because that could impact their business and could even make them liable to the government. So must revalidate in that case forces you, even if content is expired, to always serve the new stuff, never serve the old stuff. As mentioned here, serving stale content is not allowed. And again, there's flexibility for shared and private caches. Must revalidate applies to everyone. However, proxy revalidate specifically applies to the shared devices. Again, naming things is hard. Shared, proxy, whatever. But again, same as must revalidate only for proxies. Here's where I needed to do a little bit of research, and we're wading into more murky waters or more exotic territory. This immutable keyword is a very interesting one. I wanted to test it. I tested it yesterday. So let's say you put something in the cache and you want to test your browser cache. Every time I did a refresh without that immutable keyword, my browser just kept on fetching it. There was no respect in the browser for any of the caching that was done for some odd reason. We always learn about how to do hard refreshes in the browser, but even a regular refresh or just hitting re-entering the URL caused cache misses. So I was like, how is this possible? So the implementations differ, Firefox from Chrome, from Safari, from the others. But apparently the immutable keyword is supported by both Firefox and Safari and avoids refreshes. So what it pretty much does says, content will not be updated while fresh. I tested it in Firefox, I did hard refreshes as much as I could, and it didn't clear the cache. It respected the TTL, I set the TTL, in my case, to 10 seconds, and only after 10 seconds did it contact the origin again. So you could pretty much box the user in. It's a pity that not all the browsers support this, but then you could offload some of the pressure from your caches on browser cache. So immutable does that. Very useful for browser caching. If you want to make it completely immutable, that no refresh ever happens, some browsers have like an infinite TTL if you don't specify any. So you could just do public, immutable, and then things would stick around. Also in the proxy, forever and ever and ever, if you would like to do that in any case. Another one is no transform. What it means is that intermediary caches can't tamper with the content. And we like to do that from time to time. And I'm looking at the CDN folks as well. We like doing that. Let's say we want to make images more efficient. We see a PNG or a JPEG come in. We read the accept header from the browser, and we notice, hey, this browser supports WebP. Let's compress the image. Well, no transform doesn't allow you to do that. It says, don't touch it, just serve it the way it came in. So if you want to do all that magic edge compute stuff, you are out of luck. It doesn't allow it, which is great because it's up to the origin to decide what happens. Next up, cache control, no cache. I do want to hear the opinion of the crowd here. What does no cache do? Experts, please remain silent. What does this do? You said it in a very diplomatic way. It stores it in the cache, but it doesn't serve it. What it does is it requires you to do revalidation every single time. So even though, again, naming things, it's called no cache, but it does cache it. It just doesn't serve it from the cache. Here's another version. It does cache, but when a set cookie appears, the no cache comes into effect. I haven't seen this in the wild. Anyone has seen this in the wild? This type of header use? I haven't. Then we get to this one, no store. Now what? Now what we do? Any takers here? Yeah, we're getting a lot closer there. Don't store it in the cache. Never store it in the cache. And here's a typical one that you see just in case, right? Private, no cache, no store. Some people even add must revalidate. It's like, whatever language you speak here, please don't store it in the cache. We do it that way. If we see in Varnish either of these values pop up, we don't store it. Even the no cache we don't store. All right, next topic. I have 9 minutes left. Cache variations. Very interesting. We all learned that the URL is the unique identifier of an online resource, and in caching land, we treat it as such. Of course, virtual hosting and the use of the host header allowed us to host multiple websites on a single server. But there's more to it. Let's say you have a multilingual website, and you leverage the accept language header that your browser exposes. So your browser sends accept language, in my case, NL. I speak Dutch as a native language. So your application can then say, hey, that person speaks Dutch, let's just present Dutch content. But the problem is caching is first come, first served. So let's say I pop up pretty early, my language is cached, and then some French person comes up who doesn't speak Dutch, and it's like, what is this all about? And cache variations tackle that need. You can instrument the cache variation using this vary header. So the vary header is a response header. You set it in your application or in your web server config. But the value should be a valid request header. So in this case, we're ensuring that there's, I'm going to show you a diagram which makes it easier, that multiple sub-objects of that main object are used. So on the right-hand side, we have test.com/. So the URL is /, it's the homepage. The host header is test.com. And we have multiple variations. So whenever the French person comes in, the sub-object with the FR variation is used. The English person will get the EN one. And you can chain them if you want to. You can connect them all together. In this case, we do that typically emit a vary on accept encoding, which means if your browser doesn't support gzip compression, at least give him the clear text version. In this case, also language variations, and also the X-forwarded proto header, which is a header I'm quite keen of. It allows you to emit or express what the first protocol was in the chain of proxies. You might sit behind a load balancer, and there might be a TLS proxy in between, so that X-forwarded proto could either be HTTPS or HTTP. And it's important to have variations like that as well. I've seen plenty of frameworks and CMSs that use their URL structure based on that value. So if you don't do that, if you don't vary on it, again, it will be first come, first served. And maybe in plain HTTP URL will be stored in the cache, and someone who uses HTTPS will get that HTTP URL. The browser will complain about mixed content, and you're in trouble. So please do that. Last subject of the day, I'm assuming, is surrogates. Again, more exotic domains. We're going to be talking about the edge in a different way. We're going to be wading into the waters of content delivery networks who can leverage surrogates. We're talking about maybe multiple layers of caching, some of which are closer to the data center, some of which are closer to the end user. So typically, the edge in this story is no longer in the same data center, or no longer solely in the same data center as the origin server. So in that case, we move the edge a lot closer to the end user. Maybe you have multiple edges. If you have like CDNs, if you build out the CDN, it might be a very basic one, it might be an elaborate one. It'll have multiple points of presence, multiple locations. Surrogate control helps you to control that if you want. If you don't want to use the cache control header, you can use that surrogate control header. It uses maxH, but again, naming things is a bit hard in this case. So the staleness is not expressed through stale while we're validate. It just is a plus sign and then a value. It's not my fault. They support no store, no cache. There's no store, and you can bind it, and you can also say no store remote. There's no exact definition what that means. So your caches should have an awareness if they're close or further down the line, but you have an ability to control that. I don't use any of that stuff in my day-to-day life. Thank you, 5 minutes left of this. The surrogate capability header is the one I like. So surrogate capability, because the surrogate does more than caching, it can act on behalf of the server and can do multiple things. This is what I use a lot. In my caching configuration, I set the surrogate capability header with a key and a value. In this case, key equals ESI 1.0. And that pretty much says to the server, to the origin, hey, I have surrogate capabilities and I can parse edge side includes. So if you want to do that, please take control. If your application is optimized for that, and it notices that it sits behind a proxy that supports ESI, it could say, you know what, if you have surrogate capabilities, I'll take surrogate control. So please parse those ESI tags. You can use different kinds of keys. You can use Varnish if you want to address Varnish. You can actually chain all the things together. If there's multiple caches in the chain, you can say, well, by default, cache it for 6 seconds. If you identify as a Varnish server, cache it for a day. If you identify as a CDN, cache for an hour. And if you're Varnish, well then, please also do the ESI parsing. And the ESI parsing fits nicely into a narrative of, you have this website. This is my brightest, most beautiful design I could come up with, of course, with a header, a footer, a navigation, and a main page, and everything's cacheable except that bloody header on top that has either your shopping cart information or that login, welcome Thijs or welcome John, and yeah, it's not cacheable. So what you typically do is you send a separate HTTP request to it. A lot of people, when I ask them, I already spoiled the secret, we're going to be talking about HSID includes, but people tend to use AJAX calls for that and make it the user's problem, an extra round trip, and whatever happens, happens. But HSID includes, who's heard of HSID includes? Few people. Very few. The CDN people have heard about it. HSID includes is a placeholder that looks exactly like this. You can drop this in your code. It's very similar to good old server-side includes from back in the day. And you can mention an endpoint. And the cache will read that on the edge, not at the server, and will compose it. So it's pretty much a placeholder that is parsed on the edge, and the output is a composition of all these blocks. Every block can have its own state, its own TTL, and it's an excellent way of stitching things together. So you can use this and say, hey, the edge says I have surrogate capability. The origin says, thank you. I'll take surrogate control, emits that placeholder, and then the edge parses it. So that means you can expose this in your code, pretty basic, and it gets turned into that on the edge, while the rest is still cacheable. And that, ladies and gentlemen, is food for thought, and maybe for a different presentation. And that is just the tip of the iceberg. I want to talk about way more, but lovely people at SREcon only gave me like 40 minutes. I could spend hours talking about this stuff. So remember this one, every system has its own implementation to configure it. We have the Varnish configuration language, which is our own programming language that hooks into a finite state machine that allows you to control every single aspect of the cache. You don't have to use it in the majority of cases because, as I've advocated in this last 40 minutes, you can use HTTP headers to get that job done. But where HTTP headers stop in terms of capabilities, that's where a lot of implementations take over. CDNs have their own way of doing it. We have our own way of doing it. We use VCL, and if you're interested in that and you want to hear more about that, you can go to our developer portal, which has tutorials and documentation and a downloadable link to the book, which is at varnishsoftware.com/developers. Last order of business is that book. I wrote it. It contains a lot of information about what I've just mentioned, but things that go way beyond that. So if you're interested in web performance and in private CDN, go read it. Thank you for sticking around. I know you had options. You stay with me, and I'm grateful for that, so thank you.